Good morning, students. Today let us discuss oxazole. Okay. Now you can see here, this is the molecular formula of oxazole. Alright. It has got one oxygen atom, and that is at the first position, and the third position there is nitrogen atom, and there are two pi bonds or two double bonds. You can see here it is a pentagon chain with two double bonds. Okay. This nitrogen is pyridine type nitrogen. Alright. Now what is the IUPAC name of oxazole? 1,3-azole. First position oxygen atom is present, third position nitrogen atom is present, therefore 1,3, okay, 1,3-azole. So this is the IUPAC name of oxazole. Alright. Now let us say the synthesis of oxazole. The first method is known as Corn-Forth method. Okay, Corn-Forth method. So in this method is prepared by the action of propane 2-ol, okay, with the amino ethyl acetate in the presence of hydrochloric acid and hydrogen cyanide. Okay, so in the presence of HCl and HCl. You can see here HCl undergoes ionization to H plus and Cl minus, or it exists in these two forms, okay, in resonance with ions. Okay. So similarly hydrogen cyanide, you can see here nitrogen has got lone pair of electrons, and in between carbon and nitrogen there is a triple bond. Okay. This will combine with the H plus to give an adduct. You can see here HC triple bond N plus, okay, H. Now this exists in resonance, okay, with the HC plus by the shifting up of electrons. You can see over here, okay, from carbon to nitrogen. So carbon acquires positive charge and there is a double bond, okay, triple bond undergoes cleavage, so that you get what? Double bond. Alright. And then NH bond. So this will be in the close neighborhood of Cl minus ion, okay, so that you get CHCl double bond NH. Alright. Now this in turn will combine with what? The propane 2-ol, okay, propane 2-ol. Propane 2-ol contains two CH3 groups, CH3 twice, okay, CH3 twice CHOH, okay. Same molecule is written in this way, CH3 twice CHOH is written this way, okay, to show the shifting up of electrons. Alright. So electrons will move from here to here, so that there is a bond between this to this carbon, okay, so that you get an addition product over here, okay, and this will combine, okay, this will combine, eliminates a molecule of NH2 and HCl. Alright. You can see here to give another product, okay. So this will eliminate two ethyl alcohol molecules, potassium ethoxide and H plus ions in the presence of potassium hydroxide, okay, to give this product, okay, by the shifting up of electrons. You can see here, and then bond cleavage, okay. Now this will result in this product. This will combine with methyl alcohol, okay, this will combine with methyl alcohol and then H plus, okay, and then undergoes hydrolysis, okay. So this product on hydrolysis in the presence of quinoline and copper oxide with the elimination molecule of ethyl alcohol and carbon dioxide, finally you get one oxazole, okay. Now second method is from ethyl alpha hydroxy ketosuccinate, okay, with what? Formamide. So what is the formula of formamide? HCONH2. So this will react with ethyl alpha hydroxy ketosuccinate heated to 373 Kelvin to give this product, okay. So you can see two ester groups COO, okay, and two ethyl groups diethyl ester is obtained. This on treating with barium hydroxide or calcium hydroxide. You can use any one of these, okay, barium hydroxide or calcium hydroxide. If you use calcium hydroxide, you get what? Calcium salt. You can see here Ca2 plus, and this will be CO minus, okay, calcium salt is obtained. If you use barium hydroxide, barium salt is obtained. So you have to write here barium, okay. So this will react in the presence of quinoline and copper catalyst, okay. Elimination of two carbon dioxide molecule taking place from where? From here, one carbon dioxide, another carbon dioxide. So elimination of two carbon dioxide molecules take place to give one oxazole. Alright. So this is another method of synthesis. Okay. Now what are the reactions of oxazole? What is the basic character? How do you explain basic character? Oxazole is basic in nature due to the presence of lone pair of electrons on the pyridine type nitrogen. You have seen in the molecular structure, okay. Nitrogen has got one lone pair of electrons, okay, that is nothing but pyridine type nitrogen, and because of this lone pair of electrons it is basic in nature. Alright. Now second one is electrophilic substitution. Now even though oxazole has a sextet of pi electrons, complete delocalization is restricted. Now why it is restricted? Due to the presence of electronegative oxygen atom. Oxygen is more electronegative compared to nitrogen, you know that, okay. So because of this there is one complete delocalization is restricted. Under acidic conditions, oxazole forms slightly electron deficient oxazolium cation. Hence, electrophilic substitution reactions such as nitration, sulfonation, halogenation, etc. do not take place. Okay. So, oxazole does not undergo nucleophilic substitution reactions also. Now, oxazole is quite stable towards oxidizing and reducing agents. Alright. Now, next let us see thiazole. Now, you can see the structure of thiazole, molecular formula. Okay, it has got sulfur, okay, similar to that oxazole structure. Instead of oxygen you have sulfur, that's all, okay, and one more is nitrogen at the third place, that is pyridine type nitrogen, okay. Now what is the IUPAC name of thiazole? 1,3-azole, okay, with the sulfur atom and pyridine type nitrogen at the third position, okay, 5-membered ring, okay. Now let us see the synthesis of thiazole. First one is, okay, from chloroacetaldehyde with thioformamide, okay. What is the formula of chloroacetaldehyde? CH2Cl CHO. It is the chloro derivative of acetaldehyde. What is the formula of acetaldehyde? CH3CHO, okay. One hydrogen atom replaced by chlorine atom of CH3 group, okay. That's how you get what? Chloroacetaldehyde. So this will react with thioformamide. Thio is sulfur, okay. Thioformamide to give one thiazole. You can see here thiazole with the elimination of water molecule and HCl. Alright. Now second method is from chloroacetaldehyde with thiourea. Okay. So chloroacetaldehyde, you can see the molecular formula CH2Cl This will combine with thiourea. What is the formula of urea? NH2 twice CO. Okay. Instead of oxygen you have sulfur atom. Okay. In thiourea. So the formula is NH2 twice CS. Alright. So this will combine or react to give 2-aminothiazole. You can see here 2-aminothiazole is obtained. This undergoes one diazotization, reacts with sodium nitrate and HCl, that is nothing but diazotization reaction, to give what? A adduct, or you can see the addition product with nitrogen positive ion or N2 plus Cl minus. Okay. So this is the product obtained on diazotization. This on boiling with ethyl alcohol, okay, ethyl alcohol, elimination of one, the nitrogen, okay, here elimination of nitrogen will be taking place to give what? Thiazole, alright, thiazole is obtained. Next, what are the reactions of one? Thiazole. What is the basic character? How do you explain basic character? Thiazole is basic in nature, okay, due to the presence of lone pair of electrons on pyridine type nitrogen. So you can see there is a pyridine type nitrogen, this has got a lone pair, therefore it is basic in nature. The basic property of nitrogen lone pair is reduced due to the presence of the heteroatom sulfur. Because of this sulfur atom, the basic property is reduced, okay. Hence the thiazole is less basic than pyrrole, okay. It forms salts with mineral acid. Even though less basic, it will combine with acids to form what? Salts. So this is the reaction or example for that. So thiazole combines with HCl to give thiazolium chloride, okay, N plus HCl minus, alright. So thiazolium chloride is obtained. So this explains what? Basic property of what? Thiazole, alright. Now next is one reaction with the sulfuric acid or oleum, okay. Now thiazole is very resistant to substitution reactions, okay, due to the presence of two electronegative heteroatoms. Under vigorous conditions it may be sulfonated because comparatively larger pi electron density substitution takes place at position 5. Okay, so position 5 substitution takes place. You can see here it reacts with the oleum at 523 Kelvin. At 5th place sulfonic acid group introduced. Okay, so electrophilic substitution takes place at the 5th position. Okay, thiazole 5 sulfonic acid is obtained. Alright. Now next is nucleophilic substitution. Let us see which are the examples for that. First one is Chichibabin reaction. What is Chichibabin reaction? Reaction of thiazole with sodamide, okay, in the presence of liquid ammonia. Okay, this is an example for nucleophilic substitution reaction. And where is the nucleophilic substitution takes place? At the 2nd position. Okay, so Chichibabin reaction is an example for nucleophilic reaction. Okay, so thiazole reacts with sodamide NaNH2 in the presence of liquid ammonia to give what? 2-amino-thiazole. Okay. Next is alkylation. Thiazole reacts with methyl iodide, okay, to form N-methyl-thiazolium iodide. Alright, N-methyl-thiazolium iodide is obtained. So thiazole is not affected by oxidizing or reducing agents. Now next let us say indole. Now indole has got one benzene ring and one is pentagon with NH group. Okay, NH group. Now what are the methods of preparation? Fischer-indole synthesis. This is one of the important methods of synthesis. Fischer-indole synthesis of one indole. Now how it is synthesized from one in Fischer-indole synthesis. Okay. Now when phenylhydrazine and pyruvic acid is heated with zinc chloride catalyst, indole 2 carboxylic acid is obtained, that on decarboxylation, okay, gives what? Indole. Okay, finally you get what? Indole. Alright. So you can see here phenylhydrazine. What is the formula of phenylhydrazine? C6H5, okay, NH2, that is phenylhydrazine. Pyruvic acid, this is the formula. Okay, CH3CO COOH. Alright. Eliminates a molecule of water giving phenylhydrazone. You can see here an addition product is obtained by the elimination of molecule of water. Okay, this water is eliminated from here H2O, so that you get one phenylhydrazone. This on heating with the anhydrous zinc chloride, okay, elimination of a molecule of ammonia taking place. Okay, from where ammonia molecule is eliminated, one N from here, H from here and H from here. Okay, NH3 minus NH3. Elimination molecule of ammonia taking place to give what? Indole 2 carboxylic acid. Okay, indole 2 carboxylic acid is obtained. That on heating eliminates a carbon dioxide molecule. You can see here eliminates a carbon dioxide molecule to give what? Indole. Alright. So this method is known as Fischer-indole synthesis. Okay. Next method is from orthotolvadine. Now let us see how it is prepared from orthotolvadine. Indole is prepared by heating N-formyl orthotolvadine. Okay, so N-formyl orthotolvadine, on heating N-formyl orthotolvadine with the potassium alkoxide. Okay, now how do you get N-formyl orthotolvadine? From orthotolvadine. This is the molecular formula of orthotolvadine. Okay, it has got NH2 group and then CH3 group at the ortho position. So it is called orthotolvadine. It reacts with the formic acid. What is the formula of formic acid? HCOOH. Okay. So when it is heated, elimination of water molecule taking place. Okay, where water molecule eliminates from here. Okay, eliminates the molecule of water to give one N-formyl orthotolvadine. Okay, NHCH2. Alright. This on heating with the potassium alkoxide. ROK is general formula, potassium alkoxide. Okay. So here also once again eliminates a molecule of water, okay, to give one indole. Okay, elimination of molecule of water taking place. From where elimination taking place? From this here CH2 group H2 and from here oxygen. So water molecule eliminates from here. Okay, and this carbon bonds to here with this carbon. Okay, so that you get what? Indole. Alright. Now third method is from orthonitrophenylacetaldehyde. Okay. Orthonitrophenylacetaldehyde. So orthonitrophenylacetaldehyde, okay, undergoes reduction with iron powder, okay, and sodium bisulfite solution. Okay, so reduction takes place with the iron powder and sodium bisulfite solution. This is orthonitrophenylacetaldehyde. Okay, reacts to give one ortho amino phenyl acetal NH2 group will be coming here. NO2 group reduced to NH2 group. Okay, that is known as reduction. So undergoes reduction in the presence of iron and sodium bisulfite. Okay, NO2 group is converted into NH2 group. This eliminates a molecule of water or elimination of water molecule or dehydration taking place. Okay, from where dehydration? From here H. Okay, from here H and then this oxygen. Okay, and then this will combine with this nitrogen. This carbon will be bonded to this nitrogen, so that a pentagon is obtained. Okay, so this is nothing but indole. All right. Now let us see what are the reactions of indole. Chemically, indole resembles pyrrole, so it is basic in nature. Okay. So what are the electrophilic substitution reactions of indole? What is the mechanism? Indole undergoes electrophilic substitution reactions at carbon 3. Okay. This is because two resonance structures can be written for intermediate cation obtained from attack 3. Alright, whereas only one structure is possible for substitution at carbon 2. Okay. Therefore, since more number of resonance structures are formed at carbon 3 attack, so that is more preferred. Third attack is more preferred compared to second attack. Okay. You can see here attack at position 3, okay, which is the position 3, this is the position. So shifting up of electrons will take place here, therefore electrophile easily attacks here. Okay. So since this becomes positive charge, now the lone pair of electron gets shifted over here. So you get two resonance structures. You can see here, this is 1, this is 2. So two resonance structures are obtained, and finally you get one electrophilic substituted product. Okay. Now what about attack at position 2? Position 2 attack means to second position should be negatively charged, right, for the electrophilic attack. So how it gets negative charge? These electrons will be get shifted to second position, so that electrophile, which is positive charge, can come and attack here. Okay. So this will be formed, and immediately CH bond will break, weak bond, so that pi electrons will once again go back to the ring. Okay. So that you get second attack substituted product will be obtained. Okay. So more resonance structure, that means two resonance structures are formed at third attack, therefore it is more stable, whereas only one structure is obtained at attack 2, therefore it is less stable. Okay. Now let us see which are the examples for electrophilic substitution reactions. Okay. First one is nitration. Alright. Indole reacts with ethyl nitrate. What is the formula of ethyl nitrate? C2H5NO3. Okay. NO3 you can split up and write it as ONO2. Okay. Ethyl nitrate. In the presence of sodium ethoxide heated to this temperature 278 Kelvin. Okay. Third attack means third position. Electrophilic attack preferred position is third one. Correct. Therefore, nitro group attacks at third position. So 3 nitro indole is obtained. Alright. Next is sulfonation. Sulfonation is done with the sulfur trioxide in the presence of pyridine catalyst heated to 395 Kelvin. Okay. So sulfur dioxide is passed through indole in the presence of pyridine catalyst heated to this temperature. We get one 3 indole sulfonic acid. Okay. Third place, sulfonic acid group introduced into the ring. So the product formed is 3 indole sulfonic acid. Okay. Now next is halogenation. Indole undergoes halogenation in the presence of sulfonyl chloride or sulfuryl chloride. What is the formula? SO2Cl2. Okay. So chlorine is substituted in the third place. Okay. Therefore you get 3 chloroindole. Alright. 3 chloroindole is obtained. Next reaction is manic reaction. Okay. So this is also one of the important reactions of indole. Okay. What is manic reaction? Indole reacts with the formaldehyde and dimethylamine. Okay. What is the formula? Dimethylamine CH3 twice NH. Formaldehyde SHO. Okay. So in manic reaction, indole reacts with the formaldehyde and dimethylamine. Okay. To form 3-dimethyl aminomethyl indole. Okay. 3-dimethyl aminomethyl indole. So this is the product. 3-dimethyl okay aminomethyl indole. Common name is gramine. Okay, gramine is the common name. So this is known as manic reaction. All right. Now next is reduction. Reduction with nickel. Okay. So indole undergoes reduction, that is hydrogenation in the presence of nickel catalyst heated to 523 Kelvin. Okay. We get octahydroindole. Okay. Octahydroindole is obtained. So that there is no double bond, alternate double bonds in the benzene ring, as well as no double bond here in the pentagon. Okay, so NH only group in the pentagon, and here only CH group, CH2 will be formed at all the corners here, CH2. Okay, so this is one octahydroindole. At 8 positions hydrogen atoms are substituted. So therefore octahydroindole. Okay. Next is with the tin. Now when it is heated with the tin in the presence of HCl, okay, what happens? 2,3-dihydroindole is obtained. 2,3-dihydroindole. That means second place here and third place hydrogen atom is introduced. Okay, so benzyl ring remains untouched. Okay, this will remain as it is. Only 2 hydrogen atoms add up where second and third position. So that you get 2,3-dihydroindole is obtained. Okay, so I will stop at this stage. All right, please go through all these slides. Okay, so any difficulty, please contact me. Okay, thank you.